Good afternoon, everyone. I welcome you to all for the Day 5 Session 3. It is an honor to read the biodata of Mr. Guru Prasad Reddy V. Mr. Guru Prasad Reddy V received his BTech in Electrical and Electronics Engineering from JNTU and MTech in Power Electronics and Drives specialization from Vellore Institute of Technology in 2013 and 2015 respectively. During 2014 to 2015, he worked as MTech project student in NIT Bombay. From 2015 to 2017, he worked as research associate in NIT Bombay. From 2017 to 2020, he worked as senior engineer in Robert Bosch Engineering and Business Solutions Private Limited. From 2020 to 2021, he worked as senior engineer in Mercedes-Benz R&D. Presently, Mr. Reddy is working as application engineer in Infineon Technologies. I heartily welcome you, sir, for the session. Over to you, sir. Thank you.
Thank you, Anand. Thanks for briefing about myself. So let me start the presentation. Can you see the screen?
Yes, sir.
Yeah, so today we'll speak about a few things about EV industry, SiCs, how it is growing. So what are the challenges and how it is beneficial for the EV industry. So initially we'll speak about the key trends in EV industry, and at the same time what is the situation at the moment. So later on we'll speak about the EV powertrain architecture and few charging topologies, and at the same time some gate driver issues and what are the challenges in the gate drivers. So then connectivity and control security in the DC EV charging. So mostly we'll speak upon EV charging side today, and similar again in the inverter side also we have some challenges. So those I'll parallelly speak upon that. So I did not add any new slides on that. So coming to the nowadays key trends in EV market. So basically EV market is growing like anything. So especially OEM strategies and those technologies. So it's like very rapid in nature. And if you see charging side nowadays, it's a little bit challenging, tricky, and so and at the same time to improve a lot of parameters like efficiency and cost, so some regulation infrastructure side, so a lot of issues are there, but all this will address by having so many topologies uh, in EV charging side. And coming to the technologies wise, there are so many technologies which was been working in the past couple of years, maybe last 7 to 8 years. EV industry, it is growing like anything, where the EV technologies are charging side especially. There are so many technologies has been provided, and at the same time infrastructure wise it was increasing, and cost it is, yeah. So every OEM is having their own strategy. Because of that they will have cost cutting also, because to improve their products. So again cost is the very challenging now. So all these will be having one, I mean all these are main challenges from the buyer side. And if you see as a seller side, again there is a low cost product, I don't know how to make it, but to get it those one, I feel as a system side, overall system side SICs will be the very.
Sir, sorry to interrupt you. Sir, can you please minimize the small window, Teams window on your screen? We are able to see the small window on your slides. Could you please minimize it? Yeah,
Right.
Thank you, sir. Now it is fine.
Yeah.
Please continue.
Yeah, so these are the challenges from the buyer side. So again while I'm making the converter, then again a cost in the low cost, I don't know how to make it, then it's a very low cost solution. Then if you see SiC devices, I know device cost is more, but if you see overall system cost, it will be reduced. Why? Because the moment if you go with the higher frequency and higher power and all, so there the power density it is coming high, and overall mechanical cost it is reducing high huge there. So as a device cost it will be more, but other cost like mechanical bomb cost will be reduced it. So we'll see some of the challenges and some interesting points about the this SiCs. So coming to the EV market, the pollution wise and all the COT emissions it is reducing from last 10 years. If you see, it is drastically reducing in the US and Japan and China. So but the percentage if you see it is reducing very huge. Every year it is reducing 10 to 15% of CAGR it is reducing. Yeah, over the years it will reduce it, but again this efficiency and this constraints are there. Because of that we have to look into technical side as well. So coming to the EV charging side, we have different kind of charging, like in home chargers and commercial chargers, super fast chargers, like something like this three categories. If you can divide it, there at the moment it is like subunits. They are paralleling and they are giving the charging. If you take it 20 kilowatt wall mount charger in the home, they are making two 10 kilowatt chargers and it can be charged it in 20 minutes, 120 minutes, something like that. And coming to the commercial, at the moment in India, most of the chargers are 50 kilowatt chargers. So now they are moving to 150 kilowatt and all. But there also it is like it's not single unit, it's a multiple units. They're trying to make it parallel it, and because of that you will have the benefit of cost and power saving. So all other aspects are there. And one more is high power charger. At the moment 350 kilowatt charger is there, so that is for 7 minutes. So maybe it's like it's a 50 kilowatt charging, 50 kilowatt hour charging battery if you consider it. This is the charging times and all. So but there you may have the single question like this: why don't we keep it one single converter instead of multiple converters? That I can speak in the few slides after that. So now if you see CoolSiC, is it new or already implemented? Yeah, there are some of our customers, they have already worked on it. They have implemented. There is a one, if you can Google it, so maybe you may get some charging systems like this. So they have already developed the 400 kilowatt chargers, but still it's already there in US. There have 80% of SOC battery and all, it can be charged it in 10 minutes. It's like full power. It can if you take it SOC of 10% to 80%, it will be charged in 10 minutes. But again from 80% to 100%, again see it will be operated in CV mode. Then your time will be little bit more, but most of them they do prefer it this one. So it's already developed a product. Some of them are using in European. That you may see in the Google also. Maybe you can click this one in the Google. You'll get to know more information about this. Coming to the EV segment, so what are the powertrain side? How voltages and inverters will be there? So if you see EV two-wheelers and all, they will have up to 5 kilowatt rating, and those DC link voltages will be 24 volts and 48 volts. And the three-wheelers, it can be having 60 volts, and light commercial vehicles, it is again 600 volts also. So again, passenger cars and heavy trucks, commercial vehicles, those will be like 500 kilowatt and all. So cars, it is having up to 250 kilowatt. So now cars also, Porsche, Daimler, they are having SiC inverters also in the powertrain segment, not only in EV charging. So there the DC link voltages and power ratings are like this. But here, if you see from light commercial vehicle to these three segments, we can take it SiC devices as one of the main important SiC side, and all SiC device we can operate it in the inverter mode. So there, if you see EV side powertrain block diagram, it would be something like this: EV charging, and then followed by DC battery HV, something like this 500 volts. Then followed by a inverter, it will drive the motor. It will be around 150 kilowatt also. But the motors, it will be again, it will vary from vehicle to vehicle, and power to, again power also it will be vary. But so if you see inverter ratings and all, if you see, it will be 90 kilowatt to 150 kilowatt of this inverter. So so since inverters are something in this range, maybe the motors also, it will be something like this in this power range, but it will be little bit more also, because at the beginning stage and all, you may need a little bit high power to drive the vehicle. So again, this DC link voltage you can give to our auxiliary loads, 12 volts net, like side vapors, and some more auxiliary loads, lighting, and your battery charging. So it's like 12 volts net will be given in the vehicle. But again, some more converters has been there for their loads and all. So every loads, they have their own converters, like power steering, they will have the BLDC motor with 12 volts inverter, something like that. So similarly, one more power net, it will go to inverter. So it will go to compressor. So it will be again depends on vehicle to vehicle. These power ratings will be varied. So normally it's a 1 kilowatt to 2 kilowatt compressor motors has been used. But again here, it's not that much tricky. But now at the moment, these two powertrain inverter and EV charging converter, these two are main challenging. So nowadays, these DC to DC converters also, they have started working on SiC plus GaN, because the higher it is like this topology, it will be something like PSFB and dual active bridge converter. So high voltage side, they are using SiC, and low voltage side, they are trying to use gallium nitride also. So wherever these high voltage systems are there, there you can easily replace IGBTs with the SiC MOSFET. So coming to the EV charging side. So EV charging side is something like this. Grid side, you can take the power from AC, and where you need to have the AC to DC section, and followed by a DC to DC section. So those can be given to EV vehicle battery. So similarly, though, from there you need to take the data, how much it has been charged, it how much percentage and time and all. So from there you can try to give the data to your supplier, wherever you buy it vehicle. So they do credit from your credit card, something like that. So similarly, the data you can take it from the grid and BMS. Those battery storage, it can be something like this, you can take it and you can give. But this is again off grid solutions, where in your home you can replace it and you can take it. So if you see some of the high power converters and all, mostly nowadays it is going to 60 kilowatt converters also, something like this, and they are in modular fashion. So if you keep the modular fashion, what advantage will get it? So we can see in the right side. So left side, if you see, so power sizing, it was single station. So where the 75 kilowatts, it was used it as a one charging station. Though more than two, they can place it, and they can keep it as a high power station. Like if you see, if you want 300 kilowatt tundal, you have to place it five. And similarly, if you go with single one, again those challenges will be different. Charging time and other constraints will be there. But if you go with modular one, you will have the in 19 rack inch and with 1800 design. So all these can be placed it like in your lab. You might have 19-inch rack, right? So there you can easily place this one. So again, where the if you go with SiCs and all, what advantage we can see is so because of the modular design, the power level demand and those liquid cooling and all those can be reduced it huge, and because of that, the sizing will be come down. So similarly, the space also it can come down. So why? Because if you are placing one converter with liquid cooling and similarly multiple converter with the different liquid coolings, there it can be the mechanical cooling will be different. That too, you may not use all the time that 300 kilowatt. So most of the time you won't prefer it also. So if you see charging side, as I mentioned, we need to have the two stages. One, you should have the AC to DC and similar one, DC to DC. Here one more. Sorry, there is a DC to. It should be DC to AC. Yeah. So this one is a second stage, DC to DC stage. So in the primary stage, AC to DC, where you will have the three kind of topologies we have at the moment in the market. So most of the 50 kilowatt side and all, we do use VNR rectifier less than 50 kilowatt. So where the this central switches, it will be having power factor correction control. So remaining the voltage, whatever you get it, you can take it from here. So but it is not preferable for high power and all. So then again your active front end will come into picture. So again, one more is diode bridge rectifier with more than 100 kilowatt. So you do have the diode bridge rectifier with the secondary transformers. You can split it into two fashions where you will have the more less ripple, and because of that, the power factor it can be improved more. So again, secondary side anyway, you will have the your own DC to DC converter. That too depends on your power rating. You need to resize your DC to DC converter. So see all these switches, it can be used as SiCs. Again, here these diodes also, there are very good silicon carbide diodes are there. So that also can be replaced with SiCs, and you can take it these diodes. And one more thing is one DC to DC converter side. So we have the multiple DC to DC converters. So especially if you see resonant type LLC and CLLC, bidirectional and unidirectional. So phase shifted full bridge, again two types are there with the ZVS operation and dual active bridge operation. So now these two unidirectional is okay, but bidirectional also if you want you can take it. But again, it's like whether it is off-board or on-board chargers. If it is in on-board chargers, then you can prefer bidirectional one. So if you have only off-board chargers, better you can prefer unidirectional chargers. So again, these two will have their own advantages and disadvantages, but right now the debate is not on that. So if you want to make it again efficiency, size and cost, all these three, it will be trade-off. I don't know if you want to make it high efficiency system, size will come down, cost will more. Again, if you want low efficiency, size will be more and cost will be reduced. So it's again a trade-off between all these three. So if you want to go with a higher efficiency system, so better you go with the two-level system and LLC, and later you can go with the Vienna rectifier and PSFB with the ZVS operation. Similarly, in the three-level also, if you can go, but again, efficiency-wise, it will be more. So where the packaging issues will be huge there. So because of that, the size can go more, and because of that, cost will be increased it. So here the cost will decide that these three factors. It's like a general practice only. So topology and cooling mechanism and switching frequency and voltage class. So anyway, now voltage class is we cannot do anything because we have two standard voltages, 400 volts and 800 volt systems. So the switching frequency, if you increase switching frequency, magnetic size will come down. And anyway, we need to design our converters such that the cooling should be withstand that much power dissipation. So all these four parameters will decide your cost. So sizing wise, functionality and topology, packaging wise, again, it's like offboard or onboard. Again, if it is a offboard chargers, so you will have the flexibility to use industrial grade cover and all. So if it is in vehicle, again automotive standards, you need to follow it. So if it is in grid side systems, that too is offboard, so it can be industrial grade system. So that is you can able to easily classify that whichever is sitting on the vehicle, those are automotive graded. Whichever is not seated on the vehicle, so like only charger is the main component, which is the industrial grade component. Remaining all are automotive grade components. So how it is different than SiCs with the IGBTs? If you see off losses and on losses, EON and EF, if you see IGBT for a particular device, we have high speed devices with 40 amperes, and similarly we have MOSFETs with 40 amperes, similar device with the different temperature, 25 degrees and 175 degrees. So where if you take it 50 kilohertz is one of operated with, we have IGBTs also in our Infineon. So we do operate those IGBTs with the 50 kilohertz and until 100 kilohertz also. But the same device, if you want to similar part, we have compared it here. If you see off state losses and on state losses for different currents, if you see how much difference, you can assume it easily around 50% of at 10 amperes, and 10-20 amperes also it is less than 50%. 30 also it is 50%. So on state losses will be very less, and compared to here off state losses, yeah, off state losses also only uh, 3/4 of the load, 3/4 of the current, rated current, and full rated current. These two will be more, but at lower stage again it is nearly same current it is following, because of the device capacitance which we do while we are operating at while we are turning off, it will be little bit slow. Because of that, we have to give negative current there. So again, RDS on how it will be varied in the SiC devices. So if you see with respect to temperature and with respect to other devices, SI devices and GAN devices, yeah, this cool MOS and cool GAN and cool SiC, it's like Infineon products, like where we have standard names of this one. So you can assume it's a single MOSFET and SiC MOSFET, again gallium nitride MOSFET, where the temperature MOSFET, those temperature multiplication factor of that RDS on, you can take it that factor, it will be very less for the SiC compared to MOSFET and gallium nitride. So those RDS on and RDS, so RDS on is the main parameter. If we have taken three devices, which one is discrete IGBT, IPW50R07 and IMZA 5MR1, other one IGOT 60R07001. So all these three devices has been compared it here. At 100-degree temperature, we have less this multiplication factor kappa. So why? Because I already mentioned the device dynamics. It's having a device side and all. It's a very good performance. And similarly, internally we have the one more P plus layer to add it for that, to reduce it. Again, we have the trench stop also in our new technologies. So coming to the gate driver design, what is the tricky here? So as you know, RG on and RG off, those are like very challenging factors in our system. I cannot keep a very high value of RG on to reduce the EMI. Again, power loss also it will be more if we keep the more RG on. So peak currents also it can be come down if you keep the more resistance. Again, it will be slow turn on. If you keep the slow turn on, again next instant while it is having the turn on, again it will be creating some issues like upper switches and lower switches, it can be malfunctioning. Because of that, we need to provide the deadbands. But even if you provide the deadbands, if you did not have the proper RG on and RG off, then again those small shoot through will happen it there. So yeah, this RG on and RG off, it's like again a trade-off for your losses and your on time. So for that one, what you have to do, you have to do your own double pulse test and you have to characterize for your system. So your system rated current and your rated frequency and your rated voltage. So at that particular parameters, what I have mentioned, these three, so you need to turn on and turn off, and based on turn on and turn off characteristics, you need to decide the RG on and RG off. So here no such thumb. I mean, it's a similar way what you followed for the SI, what you did it for during your SI design of your IGBT. Same procedure you need to follow here. So again, layout wise, yes, it's a tricky layout here because it's a high frequency component. So because of high frequency, the loop inductance, it will be going high. So that we should try to minimize it as minimum as possible. So that layout point of view, we should take care of that. And protection side, again, desaturation we don't have, but this one I have taken it from our IGBT. Only overcurrent protection and two level turn off anyway you can use it. So ground isolation you need to have, that is anyway basic basic feature of the our SiC protection. And again, coming to the high dV by dt, and one more is tail currents, which we do get it in the IGBTs, but here also we can get, but there is different current that is very small spiky. After turn off, still one more spike current you can get it. So that you have to minimize it. So again, parasitic turn off, again I mentioned you this RG on and RG off, if you reduce it. Similarly, if you reduce the loop inductance, this parasitic turn off you can reduce it. At the same time, your DC link bus bars, whatever you have the DC link positive and negative, there are copper bars, those you have to uh, reduce those loop inductors. That you can reduce it by having some analysis in the Q3D simulations. So yeah, these are the some of the parameters. Yeah, so in the EV charger side, again some different factors like ID with respect to VGS, and RDS on with respect to junction temperature, and turn on losses with junction temperatures, and turn off losses with RDS on. So while we are doing the paralleling, we need to consider all these three. So where we are operating, how the on and off loss it is there. So RDS on, are we having enough drive current or not? Again, off losses when we do paralleling, whether it can be reduced it or not. So these all four parameters we should consider it. Again, those ID it will be varied. So that's software transconductance you need to maintain it. That band you have to calculate it while you are turning on and turning off that. So that again, software transconduction means conductance means it is like when you parallel it, the device capacitance what you get at the input and output side of the switch. So that maybe I can speak how the conductance capacitance will matter here. So one more benefit, if you have the metal they are making something fashion like this. So one is for 400 volts inverter and one more 400 volts inverter. They are connecting in the midpoint and they are trying to operate it. And after that again they are making into two separate sources here and they are adding it something like this. So because of this passion, so the current, if you see, it will be anywhere you need to make it over current, and the device count, if you will have the more in this one. So when you go with SiCs, yeah, maybe a single device you can operate it something like that, and that too you don't have 1200 volts power MOSFETs in the market. Even if you want to that, you have to operate more devices in parallel, so then device count will be more. So again, if you go with only SiC, so even single device you can operate it something like this. So so because of that, the device stress will be less, and again number of counts and bidirectional operation also it is possible with this. But on bidirectional, it's not the at the moment attractive feature. But only thing is it will be easily operated, and if you want more current, you can parallel it also this one. Yeah, so this was I was speaking about the device capacitance. So at 1 megahertz frequency, when VGS is 0, so the device capacitance will be very high. So because of that, the capacitance is low. The uh, when capacitance is low, when you are turning off, the charge it is stored in the switch will be less. Because of that, the malfunctioning it will be reduced it, and that too during ZVS operation and all, it will be very good, because while you are turning off, the voltage it will come down, and the current what you are drawing it will be already coming to the zero. Only the voltage it will be there. Sorry, I was mistaken. The voltage will be zero, the current will be somewhat, it will flowing to the device, but it will not be that much contribution in this. So because of that, less capacitance in the CASS. So coming to the again some more parameters, like when we compare with the device at RDS on and RDS on QRR, RDS QG, this charge and the reverse recovery charge and output charge. These three matters for your ZVS converter. So especially QoSS, it will be dead time when it will try to increase or decrease your dead time. So to reduce that, you need to get this QoSS as minimum as possible, and the similarly RDS on also you need to have less. So so it's again a trade-off here. So you may not have very less QoSS and again RDS. So this one you are preferable for only ZVS type DC to DC converter. So again, RDS on and QRR, these two will be matters in the PFC. Why? Because the reverse recovery time, the body diode will conduct the power factor. You can maintain unity, but again, the losses will be more when diode is operating. So we have to reduce that. So again, light load condition we have seen already. So the it's not that much beneficial here. So we need to see these two parameters, RDS on and QG. Yeah, there is one more 30 kilowatt design. If you see, there are devices which has been used it in the rectifier side. So what you see on the diodes and center point, it has been connected to our Vienna. So it's a split capacitor. In between, you have connected it to AC grid side. So secondary side, again you have the diodes. Uh, sorry, power MOSFETs, and again secondary side again diodes you have. So the power flow it will be go something like this, AC to DC. But during that time, this VNR rectifier will try to maintain the 800 volts as a minimum, so maximum it can go to 840 also. So from here you can try to reduce the voltage, or you can maintain the CCCV control strategy for your battery with this one. So here if you see AC to DC, you can operate up to 40 kHz, and similarly DC to DC converter you can operate up to 300 kHz driver. So there again, MOSFETs, you can consider these MOSFETs. So at the moment, this you can have it. Two is a parallel, so only one instead of one switch, there are two connected in parallel. So drivers anyway, drivers it's been 8 drivers it has been. So microcontroller it was used. So we have one available board in Infineon website. If you want, you can use it. So it's like an 30 kilowatt straightforward solution. You will have it. So you will have the reference design and schematic of that. So it's like a very good solution for the home usage. So it's not commercial purpose, but it's a very good solution because of its charging time and efficiency. So again, it's a air cooled converter. So but they are connected to parallel PSFBs, not one. So again, if you come to 60 kilowatt, there is a one more charging topology. You can see it here. One is AC side EMI filter and VNR rectifier. What you have, so that is different topology. And this one also you can call it a VNR rectifier. So again, DC to AC side, you will have the devices something like this. One leg it will be something like this, and secondary you will have the diode bridges. So there three phases of your bridges you can take it, and those can be converted into DC. So it's like a three half bridges converters. It's a parallel. So each bridge it will have 20 kilowatt power rating. So secondary side it can be operated as AC, and you can get it the voltages. And again you can maintain the CCCV with that. So there you will have the 40 kilohertz is the inner rectifier side, and DC to DC you will have the 120 to 140 kilohertz, where the drivers these drivers has been used, and these are the switches can be used. Similarly, diodes also something, these diodes has been used it. So this is having, these are the some features. So you may be having one doubt, why don't we have the single stage itself? But main advantage is galvanic isolation between your system and your battery. So that's again main requirement. That's why we have to maintain that. But with the directly grid you cannot have the isolation if you go with the single stage. So these are the some conclusion points which I will try to give it elaborate. So we have seen some of the SiC devices, their uh, power densities and those converter topologies we have been discussed, and some of the bidirectional operation with MOSFETs. Maybe there we can utilize it, full utilization in the 4 quadrant. Similarly, in the scalability side, if you see those discrete devices, we can go with up to 30 kilowatt. More than that, we can go with the neutral point clamp, especially VNR rectifiers and all. So again, efficiency wise in our portfolios, if you can see, it can go up to 99% so overall. So its losses will be very less. Hello.
Yes, sir.
So if you have any doubts in these topologies and all, we can discuss it some more.
Participants have any doubt on these topologies? Please ask your question if you are having any doubts. Okay, I think there is no doubt from the participants.
I would like to thank you, sir. Thank you so much for this wonderful session on EV charging, and thank you for having you here. Thank you very much.
Yeah, thank you.
Thank you for your for giving us your valuable time. Okay, so nice presentation. Thank you, sir.
Yeah, thank you. Thank you, sir.
Yes.